everyone. My name is Ankur Patel, and I'm the author of Hands-On Unsupervised Learning Using Python. Thank you for joining me today. As you know, unsupervised learning is a fairly new space, at least in terms of commercial applications, if you look at the broader ecosystem of machine learning. And before we begin, what I really want to do is explain why unsupervised learning is so valuable and really how you can use it to build applications of your own. And this is really an applied discussion, particularly around how unsupervised learning is being used by companies today to solve problems. Now, if you look at the general machine learning ecosystem, there are fairly large branches, fairly diverse and large branches of machine learning. And the one that most people are familiar with today is the branch of supervised learning. And supervised learning, as you know, is machine learning that involves labels, right? So if you have a labeled data set, you can train a machine learning model then to identify the patterns on which the machine learning model has been trained, right? So it's been coached, it's been trained on the labels, and it's able to identify more cases of the labeled data in the future. So it's able to do inference using the training from the labels that it's seen. A great classical example of supervised learning is, for example, an email spam filter, where you have emails that are spam, and then you have emails that are not spam. If you label enough of these emails as spam or not spam, you could really train a very simple supervised machine learning model. Specifically, it's a classification model that is able to then identify future emails as either spam or not spam. And I think that is very, very straightforward because it's been trained on a lot of this data. Now, unsupervised learning is very different because you don't have labeled data at all. It's totally unlabeled. And as you can see, that presents a challenge, right? The machine doesn't know what one type of class is versus another type of class, for example, if you want to make this a classification problem. But there are still ways to solve this, and this is what we'll walk through. And this is particularly important in industry because most of the world's data is not labeled, right? It's unlabeled, super messy, super noisy data. And if you only allow machine learning to operate in the supervised space, it's going to have very few applications. It's only going to be able to work on a very small percentage of the world's data. And that's why unsupervised learning holds so much potential. It's actually able to work on the majority of the world's data, find inherent structure and patterns in that unlabeled data, and then surface them up to a human to be able to interpret, analyze, make decisions off of. So I would say on the grand scheme of things, supervised learning is much more developed. It's much more ready for commercial applications because it's a more mature field. And in some ways, it's an easier field because you have the labels to work off of. Unsupervised learning is a fairly newer field, especially in commercial settings in industry, but it's the field that has the most promise long term, especially if we want to approach anything that resembles in a general artificial intelligence, right? And that's sort of where this conversation goes, is that unsupervised learning has so much potential. There are baby steps on that journey, and I'll show you one simple application that is already used today. And I think what I'll try to do is allude to why there's so much potential in the years to come with this space. So with that, let me present a couple of slides just to frame the problem and frame the space. And then what I will do is I'll move to a notebook environment and discuss the items in the notebook that really go through code by code snippet, the examples in unsupervised learning that are relevant to us. Just bear with me here for a second. Let me actually load this PowerPoint. Okay, great. So this is an example of anomaly detection. And it's going to use dimensionality reduction. So I'll unpack anomaly detection and dimensionality reduction. There are two very common things in the space of unsupervised learning. And the reason why we're starting with this application is because it's the most advanced when you look at unsupervised learning applications in industry today. And I think it's going to be very applicable to you because finding anomalous patterns in lots and lots of data is a problem. It's a troublesome point for many different companies, and so the applications aren't just in this one particular space of finance that I show anomaly detection in. It also applies in many other spaces, and we'll get to that in a second. All right, so a couple of things before we get started. What we would like to get through in this session is really we're going to talk about the complexity of data, right? So if you have very large data sets, very large data sets, you can imagine fields that are thousands or tens of thousands, in some cases millions of fields, right? So these end up being millions of columns for people that have worked in spreadsheet programs, or millions of features for people that are familiar with machine learning. This becomes a very complex problem because you talk about this very large hyperdimensional space, and it becomes very hard to find the proper solution in that very high dimensional space. So what unsupervised learning is very good at doing, using dimensionality reduction, is mapping that much larger space into a smaller space, right? So you can imagine, for example, the simplest example, mapping a 3D space to a 2D space. You can do that, and in fact, once you move from a 3D space to a 2D space, it's much easier to view the data, right? The data points become closer together in space, and therefore it becomes easier to find the underlying patterns. In much the same way, unsupervised learning, particularly through dimensionality reduction, performs that function. What this does is it helps remove irrelevant information in the data sets, right? So if you go from a very large space where there's just frankly too much white space between the various observations, by mapping it to a smaller space, you actually reduce the space, the white space among observations, and you're able to also remove irrelevant information. Because some information truly doesn't matter. Some of the dimensions may not truly matter, and so you're mapping it into a smaller space where the most important dimensions have a larger percentage of importance, right? Mapping the points into the 2D space, but the white space is gone. And then once you move to a smaller dimensional space, it's actually easy to perform anomaly detection. Because anomaly detection, by definition, you're detecting for anomalies, and anomalies are points that are by definition anomalous, so they're very different from what is normal, right? So when you move from a very large space to a smaller space, you're able to see where the points are most dense, where they most closely clustered or grouped. And that space where the things are very closely clustered or grouped is what is normal, right? The majority of the observations are in that normal space. Any points that are outliers, right? So points that are not in that really dense center, they're anomalies. They're points of abnormal behavior, irregular behavior, and those are the ones that are worth examining closer because they might be incidents of, for example, if you look at it in a finance or insurance-related problem, there might be cases of fraud or money laundering or some sort of data breach or some sort of data error, right? Those are the ones that you should spend the majority of your time solving and examining and investigating because they don't occur that often, right? They're very anomalous, very much outliers. So in this, in this short session that we have, we'll perform both linear and non-linear dimensionality reduction, and I go through this a lot in my book, but this will help you at least understand how dimensionality reduction works. Then we'll introduce a credit card data set, and we'll perform fraud detection there using dimensionality reduction and anomaly detection. And then what I really want to do is make this applicable to you for other types of problems that you go solve, right? So the intuition that we build here is going to be very important. All right, so with that, why unsupervised learning? I tried to really frame this, which is supervised learning, very mature field, work on labeled data sets. You have unsupervised, which is very large data sets, but they're unlabeled. And then there's a third branch, reinforcement learning, which is really out of scope for us for right now, but just know that that is another huge branch of machine learning that is also in somewhat of its infancy phase. And then there's the kind of the blend of the multiple areas of machine learning, which is frankly known as semi-supervised learning, which is you have a portion of your data set that's labeled, a portion of your data set that is unlabeled, and how do you marry the kind of the prowess of both supervised and unsupervised learning to really go solve problems. And that's a very important area of research because if you look at, for example, children when they're trying to learn certain things, they may have seen certain observations that are labeled in the sense that the parents tell them this is a car, this is a boat, this is a fire truck. But then on their own, they're able to find new instances of cars, fire trucks, and boats, and really incorporate that into their learning process. And then they're able to leverage that information to quickly be able to label cars, boats, and fire trucks. In somewhat of a similar way, machine learning models and machines in general need to be able to learn off of a very small labeled data set and leverage that to larger unlabeled data set in order for machines to really expand their ability to get to like some sort of AGI, right? Artificial general intelligence. And then the last comment is unsupervised learning is really good when you don't have a lot of labeled data, of course, and also when you have very large dimensional data sets. And I think these these topics and I just mentioned a few minutes ago, so this should really resonate with you, and you may have seen these types of problems firsthand with the machine learning work that you've done. Here is a list of various dimensionality reduction techniques. Now, I don't necessarily need you to define and know each of these very intimately, right? Just be aware that there are multiple techniques. And in unsupervised learning, even more so than supervised learning, you do need to do a lot of trial and error to find a good solution, right? Because ultimately, you evaluate a solution on a small labeled data set. That's always going to be the case. So even if you train an unsupervised learning model or system, you will need to label a portion of your data set to check whether the unsupervised learning model is identifying sort of patterns in the data based on the labels that you generate on like a test set. And so you do this iterative process where you set up unsupervised learning, test it, and then go back and forth. And so you do want to try various approaches as you work on your problems. And then finally, when we do anomaly detection here, we will look at a credit card data set, particularly a credit card data set where there are few instances of fraud. So there are about 284,000 credit card transactions, a very small percentage, right? Just shy of 2% are fraudulent, so 492 cases of fraud. So it's a very low incidence rate, which is problematic in unsupervised learning because if you have very little incidence of fraud, how are you going to train a machine learning model to find new patterns of fraud? And so, sorry, it's even less than 2% here. It's actually a whole magnitude less. So it's a very, very low incidence problem, which is what unsupervised learning is very, very good at. So with that, let me go ahead and share the notebook environment, and then we'll get started with the coding aspect of this seminar. Okay, great. So you should see this dimensionality reduction notebook. What we will do here, and this is very much drawn on from the contents of my book that I wrote, so there's a lot more material there. But again, I want you to have some intuition of how this works and why it's so important. So with unsupervised learning, the first step that we'll go through is dimensionality reduction. And in order to work on this problem, we're actually going to load MNIST, which is a data set of images of digits. It is a very much a classical data set in machine learning, but what we're going to do is work on it without using any of the labels. And you'll see how images of certain digits will be grouped closer together when they're mapped to a smaller dimensional space. And it does this because images that resemble the number 9, for example, look very different from the images that resemble number 3 or number 1, right? And even though we're not training the machine learning model to say these are images of the digit 9 or the number 9, these are images of the number 3, and these are images of the number 1. We're not using those labels. It's able to see patterns, the pixels, and it's able to break them down and say, images that are of this particular shape should be grouped together, and the shape happens to be the number 9. And then with number 3, it does a similar thing, which is it says the pixels of these images are very similar, so let's actually map them into the same sort of dimensional space when we move to smaller dimensions, and they're closer in space together. And that's how really unsupervised learning is able to find patterns when you map from a higher dimensional space to a smaller dimensional space. All right, so very quickly here, we import libraries. This is the first snippet. The second one, we're loading in the data sets. And then the third one, you can see the shape of the data sets. So we have a training, validation, and test data set. The data set is 50,000 large for the test and another 10,000 for validation. Okay. All right, so very quickly, let's walk through the different snippets. First, we import the libraries here, and then we'll load the data sets. And this is all available on Git, so you can actually play with these data sets on your own. And let's take a look at the shape of the data sets, right? So the shape should be very familiar for people that have worked with this particular data set. Train has 50,000 observations, 784 dimensions. Validation tests both have 10,000 observations each, again with 784 dimensions. We're going to load this data into data frames, just makes it easier to work with. And we're also able to then see the data firsthand, right? So here I just described the particular matrix that we've loaded in for train. As you can see, there are 50,000 observations. And then you can see that some pixels are actually, they're 0, so there's nothing really of importance happening. Whereas other pixels do have value. I'm sorry, other pixels have some sort of contrast, and that really designates the number. But I think the best way to view this is actually just look at the digit, right? So the first observation that we have, example 0 here, is an image of the number 5. And you can see the number 5, this is handwritten number, kind of looks like a 3, kind of looks like a 5, but this is really the number 5. It's been labeled as such. And so, there are many more observations of various numbers, but this is the challenge here, is how do you actually group these numbers together in a lower dimensional space, or how do you map them together in a lower dimensional space? So all the number 5s and all the number 3s and all the number 9s are in the same space when you move from a higher dimensional space to a lower dimensional space. So there's some code here to view the digits and to do one-hot encoding, which allows us to actually go and train some of the machine learning models and systems that we work on. And so what we've done is that we have given an array to each and every single digit. So in this case, for example, since this is a number 5, the first observation that we saw, the one-hot array here would be a 0, 0, 0, 0, 0, 5, 1, so designating the digit 5, and then the rest of these would be 0. Right? So if this were an image of the number 1, you'd have an array that was 1, and then the rest would be zeros, right? And if you had an image of the number 1, then the second instance here would be 1, and the rest would be zeros, right? So the way it works is that this would be 0, 1, 2, 3, 4, 5, etc., to designate which number was in that particular image. But let's just move to unsupervised learning, because I think this is where the majority of the conversation should be in terms of the interesting topics that we have. So the first type of dimensional reduction that we will do is called principal component analysis. And what principal component analysis does is it takes data from a high dimensional space and maps it to a low dimensional space. And it tries to do this by reducing the highly correlated dimensions and collapsing them into a singular dimension. And the beauty of dimensional error reduction using PCA is that the first few components of PCA are the ones that have the most importance, right? They have the most relevant, most salient information about the data that you've just had performed dimensional reduction on. And so you can see that the first few components of the majority of the information, as you get to sort of a higher and higher number of components, they actually have less and less interesting information, which means that the first few components, like let's say the first 10 components, have such rich information that we could use just that to figure out the structure of the data, and we could actually throw away the majority of the dimensions, right? Because initially we start with 784 dimensions. Now we're able to go to a much fewer set of principal components. So we perform dimensional reduction here. You can see we use a fit transform method of scikit-learn, and then we just place this into a data frame. And then once we're in a data frame, we could see that the variance that's explained by all 784 principal components is basically 100% here, right? So if you look at 784 principal components as 100% of the information, just like the original 784 dimensions of this data set. But here's the interesting part. Here's what I was alluding to, is that the first few principal components have the majority of the interesting information, right? So the principal components here, you can see the first 10 principal components has 48.8% of the information that's relevant for this data set. And by the time you get to about 100 principal components, it has over 90% of the interesting information. That means that components 300 and beyond have less than 2% of the information that truly matters, right? So again, you're reducing noise. You're moving from a high dimensional space to a lower dimensional space, and you're retaining the majority of the information in fewer dimensions, which makes the machine learning problem much simpler, right? So this is a great pre-processing step for a lot of applications, but it's also a great step to find the inherent structure of the data. And right now we're going to look at the structure of the data for this digits data set. So you can see the first principal component here, which I show 0, has nearly 10% of the information that's relevant for this data set. The second principal component has about 7.5%, about 7%. The first two principal components have nearly 17% of the interesting information for this data set. So let's map this actually to just 2 dimensions. That means using just 17% of the information mapped to these 2 dimensions, let's see if we can find some separation in the images of the digits. And let's create a scatter plot for this, right? So this is a scatter plot of observations that occurred on PCA. And what you'll see is that the labels, so 0 through 9, are the labels for the images. Now, the machine learning model didn't have these labels, right? So it wasn't trained on labels. We're actually just overlaying labels after having trained the PCA, right? Having fit the PCA here, which means that when we look at the digits, so the images in a lower dimensional space, you can see that all the zeros are grouped together very tightly in low dimensions, in 2 dimensions here. The number 1 is right here. Okay? All the images of number 1 are right here in this orange layer. The images of number 2 are again very close in a lower dimensional space, which is this green section, okay? And vice versa, right? Or etc. So the goal here, as you can see, is that we took all of these images in a 784 dimensional space. We actually forced them to be mapped in a 2-dimensional space, and you can see that a lot of that information that was relevant in very high dimensions was retained in fewer dimensions. And as we move from dimension reduction to anomaly detection, what we're trying to identify is these anomalies, these outliers, when you look at the data in a fewer set of dimensions, right? So, for example, this is somewhat of an outlier. This is somewhat of an outlier, right? So the points that are like stragglers, the ones that are alone on the edges, they're the anomalies, quote unquote. Although, the separation of the data here is not so massive, so you can't technically say these are anomalies, but they are somewhat distant from the normality, the density of points that you see in the middle. Okay, and that's where anomaly detection comes in. But before we go to anomaly detection, let's just quickly go through more of dimensional reduction. You can see that if you took the original data set and mapped it to 2 dimensions, you actually don't retain a lot of interesting information. This is a mess, right? So before dimensional reduction, this is how a machine, or even us, would view the data. There is no inherent pattern or structure, which is very, very problematic. But PCA allows us to find that inherent pattern. That's what unsupervised learning is very, very good at. The rest of this notebook goes through various other approaches of dimensional reduction that I alluded to, that I mentioned in the PowerPoint presentation, the PDF file that I shared earlier. This is incremental Pca. You see a very similar result. Sparse Pca, you see a slightly different result, but again, very much mapped where you retain some of the inherent structure. This is kernel Pca, singular value decomposition, SVD, which is very similar to Pca. And then Gaussian random projection, sparse random projection, and then some basically nonlinear methods of dimensional reduction, including isomap, MDS, which is multidimensional scaling, again finding very interesting structures with a completely different approach of dimensional reduction. This is also a very interesting approach, LE, which is commonly used in certain sets of problems in industry today. TSNE, which you might also be familiar with, this in some ways organizes the data as clusters, right? So it is able to find some of the clusters immediately. Dictionary learning, which we'll view in anomaly detection, and then independent component analysis. Okay. So this is the entire notebook for dimensional reduction. There's a lot of information here. A lot of this information is covered in my book, so I don't want to spend too much time, because I think the main point that I want you to walk away with is dimensional reduction allows you to move from a higher dimensional space to a lower dimensional space while retaining the majority of the important information And it makes it easier for both us and machines to find inherent structure, to find inherent patterns in the data, right? And as we move to anomaly detection, you'll see why this matters so much. So without further ado, let's move to anomaly detection. And for this problem in particular, we will look at a credit card data set. Now, this is a real credit card data set that is full of European credit card transactions. And as I said, there were 284,000 credit card transactions, 492 of which are fraudulent. Now, this is a very common problem, right? If you look at insurance fraud, you look at credit card, wire fraud, online fraud, there are a lot of transactions. Only a few of them are worth investigating for the bank, right? Or worth basically rejecting as transactions. This is also very true in the world of money laundering, where certain individuals, they open up bank accounts to launder money. Maybe they're laundering money because they want to evade taxes. Maybe they're involved in bad activities such as arms trafficking, human trafficking, guns trafficking, just bad behavior, right? And what the bank needs to do is identify these like abnormal accounts or sending transactions to dangerous places, to dangerous individuals, dangerous companies, and is able to flag them and say, investigate this because we may want to shut this account because we want to prevent bad actors from being basically customers of the bank. So this is a very common problem in insurance. This is also a common problem in retail. So in retail, for example, you want to find the breakout patterns in your user base, in your customer base, particularly in your product base, like which products. If you have Amazon, right? If you operate Amazon as a marketplace, you have Amazon. You want to know which users are buying which sort of products and see the anomalous behavior because the breakout patterns are most interesting and they're the ones that are worth acting on. Okay, so anomaly detection is a very common, very important problem in industry. So here, what we'll do is we'll import the libraries, we'll load the data set, it's a credit card data set, as I mentioned. What we'll do is we'll scale the features so they're all on the same scale. Now, this is a very common task in machine learning to perform feature scaling before we use any of the dimensionality reduction techniques. And this makes the problem more tractable. It's easier to find patterns and such, and that's why we'll move there. And then we'll also define two functions. Anomaly Score is basically taking the data once it's been mapped to a lower dimensional space and is identifying which of the data points have the highest reconstruction error when you look at the reconstructed data point versus the original data point. And the ones that have the highest error, highest loss, are the ones that were anomalous, the ones that the dimensionality reduction technique didn't retain enough information on because it wasn't part of normality, right? So think of this as the outlier score as well, the anomaly score, outlier score, and then we just define a function to plot the results, and we'll introduce this as a scatter plot. So let's just move to PCA because this is going to be very relevant for us. PCA, as we saw, maps data from a higher dimensional space to lower dimensional space. And with anomaly detection in general, you actually don't want to use all the principal components to reconstruct the data. You actually want to use fewer components to reconstruct the data because by using fewer dimensions, fewer principal components, you're forcing the model, this approach, it's not a model per se, but this approach, you don't want the approach to 100% authentically create the original data points. You almost want it to forget the information for certain data points because the information that it forgets is going to be the information that's related to the anomalies, right? And the anomalies means that they are not part of the dense center and they will have the highest reconstruction error. So this data set, the credit card data set, has 30 principal components originally. And when we map it to a smaller dimensional data set or a smaller set of dimensions, in this case too, you can see that the fraud cases, the ones that are labeled as 1, appear in orange here, and the ones that appear in blue, the 0, appear elsewhere. So you can see that the zeros and the ones, they overlap to some degree, but there is some structure that the dimensionality reduction method was able to identify. And then when we reconstruct the data set, you see a precision, average precision of 11, which means that, if precision recall basically says of the fraud that exists in this data set, how much of this fraud were you able to identify? And precision gives you a sense of how precise you were, right? So how many false positives did you see? You can see that this average precision here means that in order to identify 40% of the fraud, you had an average precision that was about 0.1, which means that 10% of the cases that you flagged as fraud were truly fraudulent. Now, that's not a very good result. You can imagine if you were a credit card company and you rejected 100 transactions, 90 of them would be actually false positives. They would be perfectly fine transactions that you rejected, and that leaves a very bad customer experience. So this is a poor result. You're only getting 10% precision in the credit card transactions that you reject. So this is not very good. Why did this perform so poorly? It's because we used all 30 principal components of the original 30 dimensions to reconstruct and to evaluate the loss for this problem set. Okay? So as I said, you want to use a fewer number of principal components, because by using a fewer number of principal components, you actually cause the model to separate the normal points from the anomalous points. So here in the next problem, we're actually using 27 principal components. So you actually lose 3 principal components, which in this particular problem is enough information to lose that allows the solution to find the anomalies from the rest. Okay, and then when we map this into this 2-dimensional space, you see a larger degree of separation. And when we've mapped the precision recall, you're able to see very great precision recall. What this curve is telling you is that in order to identify 80% of the fraud, you only had, so you had a precision of 80%. That means that of the 100 transactions that you found, 80 of them were truly fraudulent. Out of the 100 transactions that you rejected, 80 of them were fraudulent. That means only 20 of the transactions that you found as fraudulent were truly not fraudulent. This is a good result. As a bank, you're much more willing to accept this level of precision recall, right? The ability to identify 80% of the fraud as, of the 80% that you reject, of the 100 transactions that you reject, 80% of them are fraud. Now, that's a very, very good result. That means your customers aren't getting angry at quite as much, because only 20 of the 100 had truly non-fraudulent transaction activity. So this is what we're trying to do with anomaly detection and dimensionality reduction, is that we're trying to find an inherent pattern without labeled data. This doesn't use any labeled data at all, right? We're overlaying the fraud that we have on this data set to verify that our solution is working as intended. Now, the rest of this notebook actually goes through other dimensionality reduction techniques, okay? And it finds the precision recall curve. Now, you see that the precision recall curve isn't uniform, and sometimes the solutions aren't actually as good. And you know that because you're using a small labeled data set, a test data set, to verify the goodness of this anomaly detection solution. And that's what anomaly detection is all about. It's about trial and error, where the majority of the data is unlabeled. You're using a small labeled data set to verify how good that solution is, right? So this solution that has 42 average precision is not quite as good as the one we did earlier, but it is helpful, right? 69 is much better, so independent component analysis is a much better solution. And then it walks through a few more. In this one particular, when we use the solution we designed on the test set, you get an average precision of 70, which is a very, very great solution, especially given that you do not use any labels for this particular problem. Now, there's a lot of ways to go and solve anomaly detection. We only explored a few, but the idea that I want to drill home is dimensionality reduction is good for mapping high-dimensional data set into a low-dimensional space. Then you find an inherent structure in that small dimensional space, and in that inherent structure, you're able to find what is normal versus what's abnormal, and the abnormal is what you then use to build an anomaly detection solution. And so with that, if you have any more questions, please feel free to ask. If I don't get to you immediately, I'll get to you via email. And then for those of you that haven't read the book or seen the code on GitHub, there's a lot more material in unsupervised learning, also in anomaly detection, and I think the best resource is actually the book itself. So please turn to the book if you have any more questions, but also please feel free to reach out to me, and we'll go from there. Thank you again.